Okay, let's get started. So first of all, a reminder that we have our midterm project report due on this Friday. So please do submit your report and including the points we have previously emphasized, right? So don't worry that you have failed to get amazing result. That's totally fine if your performance or whatever other accuracy measurement is not good. We just want to learn how what you have done, what's your plan, and blah blah blah, right? So just take a look at our course webpage, our syllabus, look at the requirement for the midterm report. If your report covers, I guess the 3 points we mentioned in the course webpage and syllabus, you will get a full grade. Right? But don't submit nothing. If you submit nothing, there won't be any point. Okay, so let us continue with support vector machines. So in the last lecture, we talked about the motivation of support vector machine. Okay? So we know that according to our agnostic learning setting, the generalization error is upper bounded by the training error plus some term related to the VC dimension of hypothesis space we use to search our classifiers, right? So if we want to develop a linear classifiers, unfortunately, the VC dimension of a linear classifier is fixed, right, given the total number of features you're going to use in your problem. So then how can we develop a better linear classifier learning algorithm such that to make this upper bound to be as small as possible? Right? One idea is to not search over the entire hypothesis space for the linear classifiers. Instead, we just look at a subset of linear classifiers, right? If you just look at a subset of linear classifiers, you search over that subset, then we have a chance to decrease the VC dimension and tighten the bound, right? Because the smaller the VC dimension, the smaller this term, and the more likely you're gonna decrease the total bound, right? So then how can we pick up a subset of linear classifiers? We use the margin, right? So we define a subset of linear classifiers that separate the training set by a margin at least a gamma, right? We pick up these linear classifiers, right? And to look at what is the VC dimension. Okay. So there have already been a theory, a lemma, showing that the VC dimension for such a margin indexed linear classifier subset is upper bounded by this guy, right? And from the right-hand side, we can see that the larger gamma, meaning the larger margin you choose, right, the smaller the VC dimension you have, right? Because the margin gamma here is in the denominator, right? So that actually tells us that, okay, if you can maintain the same level of the training error, I should pick up the corresponding gamma to be as large as possible, right? Or in other words, I should search linear classifiers whose margin is as large as possible. That motivates our learning principle. That is, we should learn a linear classifier that maximizes the margin. Okay. This is our training principle. And then we look at how we formulate a training objective function to implement this so-called margin maximization principle. Right? How can we do that? Right? First, from the definition margin, we know that it is the distance of the closest point in the training set from the classification hyperplane, right? So that means to compute the margin, we have to do a minimization over the whole training set. Just to compute the distance between every data point and your classifier's hyperplane, and then you pick up the minimum value. So this is the distance, right? So it's the distance, the formula of the distance. And in the outer side, right, in the outer level, we just maximize this minimum distance in terms of W and B. Remember, W and B determines the classifier and also the position of the separating hyperplane. Right? So here, the distance, we know that it is a ratio between the classification score multiplied with the label divided by norm of the weight vector W, right? So the classification score here, I mean, the numerator is usually called functional margin. Just keep it in mind because for convenience, later we'll keep revisiting this term, the numerator term, and I don't want to use a long phrase to explain that. I just call it functional margin. Okay. And the gamma itself, that is true margin, is also called a geometric margin because it has a clear geometric meaning, that is the minimum distance between the data point and the hyperplane. Right? But then there's a problem. Right? This naive formulation actually leads to a bi-level optimization problem. Right? Maximize. In the inner level, you have to do a discrete optimization. You have to enumerate every training example to look at which one gets the closest to the hyperplane, right? And in the outer level, you have to maximize this minimum distance in terms of model parameters, right? So this is a really challenging problem. It's a mixed discrete and continuous optimization problem, right? So our next work is to simplify this problem, right? But don't really want to do this bi-level optimization. Right? How can I do this? So here, we're going to leverage a very important insight of linear classifiers, which we have emphasized many times. The key is that for the same classification hyperplane, right, no matter how you skew the model parameters, so here the model parameters include B and W1, W2, right? You can do any proper scaling by, say, any positive number, right? 0.1, 0.01, 1,000, 10,000, 1 million. It doesn't matter. It won't change the classifier at all. Right? Any point which was classified as positive after that kind of scaling, it will classify as positive, right? Will never change, right? So that means if you search or if you optimize your model parameters WB in the entire space, entire possible value range, you actually search a lot of duplicated classifiers, right? For example, a pair of WB is totally equivalent to a pair of 10 times WB, right? It doesn't change at all. So that means it's unnecessarily for us to really search the entire range of WB. Right? We can try to restrict the range of search, restrict the WB's range to search so that we can get rid of this bi-level tricky optimization problem. That's the idea. So how do we pick up a small subset of WB so that I can get rid of the inner minimization problem, right? We can try to scale down or scale up WB so that the numerator is simply 1. Okay. Look at here. The margin is the minimum distance between the closest point and the hyperplane, right? So we know that the WB actually can be arbitrarily skewed by some positive number, right? We can multiply by 10 or you can multiply by 0.001. It doesn't change the classifier at all. Or in other words, they're equivalent to the same classifier. So now, then why not we just restrict the minimum value of the function margin? Let me repeat again. I will just restrict that the minimum value of the numerator to be 1. Right? It doesn't matter at all, right? Because for any WB, if the minimum numerator here is not 1, you just skew on WB properly, so you can make it to be 1, right? So now I put an additional constraint, right? I want to look at all W and B pairs whose minimum numerator here is simply 1. Then the benefit is that I know the minimum value of the numerator is simply 1, right? I don't need really enumerate all xi and yi's and take a look who is minimum, because I know the minimum is 1. Then the margin is simply 1 over the norm of W. This is just the formula. You got a hyperplane which defined by W transpose xi, x plus b equals to 0, right? If you want to compute the distance between any point and the hyperplane, this is the formula. Yeah. No. Later we'll talk about B cannot be ignored. We'll come to that point in a minute. But does it make sense? Like we put this additional constraint, right? We restrict WB in a subset such that the minimum functional margin, namely the minimum of the numerator here, is simply 1. Because for any WB whose minimum function margin is not 1, you can just do some proper scaling to make it to be 1, right? They're equivalent. Right? I don't really care about those WBs whose minimum margin is not 1. Right? And the benefit here is that because I make restriction, right? I constrain that, okay, this minimum functional margin is 1, so that I don't really need to do the minimization operation here, right? So I only need to, I know that the gamma, the margin here, will be 1 over the norm of W. And then what I need to do is just do the outer level maximization, because I want to maximize margin. Is this idea sensible? Everyone feels comfortable? Right? That's the key. That's the key idea how we construct SVM objective function. Okay, so now let us try to formulate the learning objective, right? So first, maximize the margin will be 1 over norm of W. So you maximize this margin is equivalent to minimize the norm of W, right? Because you're maximizing its inverse, right? So we can change the objective will be minimize half of the square norm of W, because minimize norm is equivalent to minimize the square of norm. It doesn't change the optimal at all. And then we need to consider the constraint, because the precondition that we can simplify our optimization to be like this is because we restrict the range of WB to be the set that whose minimum function margin is 1, right? So that means in our objective function, we have to specify this constraint, right? This constraint will be, okay, the minimum function margin is 1. So that means just for every training example, this function margin will be no less than 1, right? Does it make sense? This is just saying this, right? For every training example I, we have this function margin, which is numerator, right? Is no less than 1. That means minimum is just 1. Right? And here now, going back to your question, so you can see that although B doesn't show up in the objective function itself, it shows up in the constraints. So you cannot ignore it. Any questions so far? Or sounds straightforward? Okay, so yeah, let me emphasize again, right? So minimize the square norm of W is equivalent to maximizing 1 over norm of W, right? And this 1 over norm of W under our constraints will be just the margin, right? And here a set of constraints here is to specify our restriction of the WB values from which we're going to search. That's how we formulate the support vector machines training objective function. So essentially, we have convert our margin maximization learning principle into a constrained optimization problem, right? So if we want to learn our model parameters W and B, we're essentially trying to solve this constrained optimization problem. Does it make sense? Any question? And this is called a hard SVM, hard support vector machines. Why it's called hard SVM? Because you're going to assume every data point is linearly separable, right? You can correctly predict every training data point, right? Otherwise, you cannot satisfy this constraint, right? And so this is very important because we use the inside here. We use the property of linear classifiers. That is, any linear classifier is invariant to scaling. I mean, scaling by some positive factor to convert the naive bi-level optimization problem into a one-level constraint optimization problem. So that's the key idea, right? And you see that solving this constraint optimization problem is much easier than directly solving the bi-level optimization problem. So hopefully everyone will feel comfortable about this conversion, because this is the key for us to understand the support vector machines. Any questions so far? Okay, great. Yeah, so it's very good because every time when I talk about this, there are always some questions, but this time I didn't see any questions. It looks like it's easier for you guys here. Okay. So regarding how to solve this optimization problem, we'll talk about that later, right? But let's look at this part of SVM again, right? So our objective itself is half of the square norm, right? And then we put additional constraints over every training example. That is, every example has a function margin, namely the left-hand side, left-hand side of the of this inequality is at least one, right? So this will only have solution when the data is linearly separable, right? If the data is not linearly separable, that means you cannot find a particular WB such that every example can be correctly classified. That means there must be some example whose function margin is negative, right? So that means there must be some example who doesn't satisfy the constraint here. In that case, the hard SVM becomes an infeasible problem, and there won't be any solution, right? Then how can we overcome this problem, right? We know that in practice, you cannot make such an ideal assumption, right? You cannot assume, okay, your data is always linear separable, right? And what if we want to apply our support vector machine idea on non-linearly separable data, right? Or some kind of almost linear separable data, right? So we need to make proper adjustment of our learning problem formulation, right? So here is the idea. So we kind of compromise the data, right? How can we do this, right? We know that when the data is not linear separable, right? So we give up the idea to find a separating hyperplane. Instead, we want to allow some example to break into the margin. For example, here are two sets of examples, right? Positive and negative. We know that they are not linear separable. Then we can kick out some examples, right? And the remaining majority will still be linear separable. We just maximize the margin for the remaining majority. That means the outliers here will be allowed to break into the margin. Okay. We want our new formulation to automatically find out such outliers. And meanwhile, to max the margin for the remaining majority who is still linearly separable. Does this make sense? In other words, like, suppose this data set is not linearly separable, right? So our assumption is that, okay, I can automatically pick up a few examples and just kick them out. Then the remaining data points, I believe, is linearly separable. I just maximize the margin for the remaining data points, right? And the outliers which are kicked out, well, I don't care where they stay, right? They can break into my margin. They can be misclassified. That's fine, right? This is kind of compromise, right? Any question regarding this idea? Yes. Yeah. The function margin could be less than 1, could be even be negative. It is possible, right? But the idea is like this, right? I want to have some elastic and automatic mechanism such that I can identify a few outliers by kicking them out. I just maximize the margin for the remaining examples who we believe is linear separable, right? And for those outliers which are kicked out, well, they can break into my margin. They can violate the constraint I specify. That's the idea. Mm-hmm. Yeah, that's why I said this must be an automatic procedure, right? You can automatically pick up which example you should treat as outliers and kick them out, right? We need to formulate as an automatic optimization problem to do this, right? Rather than you pick up manually.
So it's showing like where we can take this quality of error where we can kind of like have this term where we modify our uncertainty, right? But that really valuable in practice because
well, here we didn't use like uncertain quantification to do this. We're gonna convert this selection of outliers and maximizing the remaining points margin by some optimization procedure. This is what we are going to discuss in the next step. Yeah, but this idea is reasonable, right? Right. The key is how do we fulfill it? Okay. The idea is as follows. To allow any example to be selected as an outlier, right? Because I don't know which example should be the outlier, should be kicked out, right? So I'm gonna modify the constraint by introducing one slack variable Ci for every example I, right? So now I modify my constraint for every example I as follows. I now put my constraint to be the function margin to be no less than 1 minus the slack variable Ci. And also the Ci must be non-negative. Right? So what does it mean? It means that if your optimization give you the result that your Ci is 0, that means your example I will still have the function margin to be bigger than or equal to 1, right? That means it's still on the margin or out of the margin, right? So that means your example are not kicked out, right? However, if your Ci is absolutely bigger than 0, right? So that means your constraint becomes your function margin is only no less than 1 minus KCI. It could be less than 1. So that means allow your example I to break into the margin. In that case, that example actually is selected as outlier. Right? So you can see that by introducing additional slack variable KCI, we enables a kind of flexibility, right? Any example might be picked up as outlier and kicked out during the margin maximization, right? Or preserved, right? It depends on the optimization. And then my new optimization problem is defined as follows. So this is a set of new constraints, right? We introduce the slack variable KCIs, right? And the different choices of KCIs will lead to different selection of outliers and non-outliers, right? And in the objective, I add my margin-related term, which is half of the square norm, plus the summation of all slack variables times a hyperparameter C. So now I have a question. Why should I just add this additional term in our objective function? Right? Why not just introduce KCIs in the constraint and then just minimize the square norm, which just, maximize margin? Any thought? Let me repeat, right? Why should I add an additional term, like this, the C times summation of the slack variables in our objective function, right? Why not just because introducing slack variables can enable some kind of automatic selection of outliers, right? And then now I have already specified this automatic mechanism, right? Why not I just maximize margin? Right? Why should I introduce an additional term in objective? Yeah, I think your point is close. Can you be more clear? Mm-hmm. 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 Yes, yes, yes. Yes, yes, yeah, yeah, exactly. Okay, let me speak it loudly, right? Okay. Why should I include this? The reason is that if I don't do this, let's see what will happen. If you look at this example, right? So if I don't do this, if I just purely maximize margin with the flexibility to kick any examples out, right? Then what my algorithm will do? I just kick most of the examples, right? And I just leave 2 points, which is furthest, right? And for example, I might just pick up this one and this one. I just look at the margin, which separate only 2 points, which are furthest away, right? I can maximize margin for sure. But then I view all the remaining points as outliers. I allow them to break into margin. That means I can make a lot of mistakes in predicting their labels, right? And then if we look at the generalization error bound, the generalization error bound consists of 2 terms. One is the training error. The other is a term determined by the base dimension, right? So although doing that, I kind of like decrease this term a lot, right? Because I maximize margin. I make my margin as large as possible. But because meanwhile, I have already allowed too many examples to break into margin, I can imagine my training error increases largely as well, right? So now, if I add them together, they won't necessarily give you a smaller bound. So you can see that the best choice should be the best trade-off between the training error and this term determined by VC dimension, right? So that means you shouldn't allow too many examples to break into the margin. Because if you break into the margin, then it is likely that you're gonna increase your training error. You're gonna misclassify those training examples and increase your training error. Right? Does it make sense? That's why we should add this addition term, because KCI, when it's absolutely bigger than 0, it means, okay, this example is allowed to break into the margin, then you have a chance to misclassify. You have a chance to increase the training error, right? I want this summation to be as small as possible. That means I want as smaller number of training examples to break into margin as possible. I don't want too many examples to break into margin, so that I got risk to decrease to increase my training error. Oh, sorry. This should minimize WB, and also KCIs. That's a type. These are type of it. So the whole optimization will be okay. I'm gonna minimize WB and KCIs. Right. So you can see this is essentially a kind of like trade-off, right? On one hand, you want to maximize margin for a subset of training data points, right? On the other hand, you don't want to exclude too many training points, because if you exclude them, if you allow them to break into the margin, you have a larger chance to increase your training error, right? And because both the training error and the VC dimension are important for your generalization error bound, you want a good trade-off. Does it make sense? Any question regarding this formulation? Okay, great. Right. And here, C here is a hyperparameter. Right? You have to specify, you have to tune it. Right? So now we have come to our more generally used support vacuum machine formulation. It's called soft SVM. Why it's called soft SVM? Because it can apply to any data set, not necessarily to be linear separable. If even your data is not linear separable, it's totally fine, right? Because it can dynamically, automatically pick up a few data points, excluding them, and then maximize margin for the remaining data points, right? And also allow some kind of trade-off, right? I don't want too many data points to be excluded to break into the margin, right? So that's why in my objective function, I maximize margin. Meanwhile, I kind of minimize the total slack, namely allow as few examples as possible to violate margin. Okay. And then this hyperparameter C represents the trade-off between the two terms. Okay, so before we talk about how to solve this constraint optimization problem, any questions so far? Mm-hmm. Yes, exactly. Yeah, you're right. So, yeah. Usually people don't use SVM as a base learner for data boosting, because data boosting works best when you have a very weak classifier. SVM is typically a strong classifier, right? So it won't work very well. Yeah. Okay, so let me come to your point, right? Actually, different setting of C represents different, well, importance or weighting you will the data fitting, right? So the larger C means that you don't allow. The larger C means that the more examples that break into the margin will get larger penalty, right? Because you are minimizing this objective function. So that means, okay, I want fewer examples to break into the margin. Right. On the other hand, if the C is very, very small, right, that means, okay, I kind of allow many examples to break into margin because their summation even is large because they multiply a small constant C. It doesn't change the objective too much. Right? So you should manually select C to make the best trade-off. Right? Later we'll talk about a general framework to choose such a C, which is called cross-validation. Okay, any other question regarding this soft SVM formulation? Okay, great. So now let us look at how we solve this problem. Right? This problem is not straightforward at the first step because this is your objective function, right? And also we have some additional constraints, right? For every training example. For every training example, you got two constraints. One is function margin is no less than 1 minus KCI. Second is KCI is no less than 0. So let us try to simplify this problem a little bit, right? First, we notice that every example, the constraint can be represented in terms of the select variable KCI. Okay, do that, right? The first constraint, the function margin, no less than 1 minus KCI, can be represented KCI no less than 1 minus the function margin, right? You just move KCI to the left-hand side and function margin to the right-hand side, right? And second constraint is that KCI is now negative. And remember, in our objective, right, we want to minimize the summation of every KCI. Right? We know the KCI has two lower bounds. And when KCI can take then what is the minimum value KCI can take? Let me repeat, right? So from the constraint, I can derive KCI has two lower bounds, right? One is 1 minus function margin, the other is 0, right? And in our objective, we want to every KCI to be as small as possible. Then what is the minimum value KCI can take? But you also have it's no less than 0, right? Yes, exactly, right? Because KCI must satisfy these constraints, right? And if you look at the minimum value KCI can take, at the same time, simultaneously, it satisfies two constraints. Then the minimum value of KCI would be it's not minimum, it's maximum between 0 and 1 minus the function margin, right? In that case, this is the minimum value KCI can take because you have to make sure that KCI satisfies both constraints. And in that case, you can just substitute KCI for its minimum value in the objective function. No, this is not a dumb question. This is a very good question. We're going to come to that point very soon. Yeah. Yeah, you see that actually, even you make a correct prediction, it is still possible that 1 minus function margin to be positive, right? So that means you still suffer some penalty. That's some kind of uniqueness of small emissions. Okay. And we'll come to that point in a minute. Okay. Another question. Okay. So you can see that from this constraint optimization problem, we kind of simplify it by eliminating the constraints. How can we do that? Because from the constraint, we know that KCI must has two lower bounds, right? To satisfy the two lower bounds simultaneously, the minimum value of KCI can take will be max of the two lower bounds, right? And once you take KCI to be that value, you automatically satisfy these constraints, right? You can just throw them out, right? And you know that you just need to minimize this square norm half plus this guy only with respect to W and B, right? So now we have converted this soft SVM objective to an unconstrained optimization problem. Everyone's comfortable, right? So now let us look at the structure of our new objective. Right? So we can see that first, this is an unconstrained optimization problem. We don't need to care about QCS because we have already found their minimum values, right? And then we see that this objective consists of two parts. One is half of the square norm of W, right? The other is a summation over every training example, right? For every summon is the maximum value between 0 and 1 minus the function margin, right? So you can see that the second term actually gives us some penalty for the prediction, right? So we can consider three cases. First, for any example, I, right? If it can correctly classify, and also is outside margin. So that means this function margin will be bigger than or equal to 1, right? So 1 minus the function margin will be less than or equal to 0. So the max between 0 and that value will be just 0, right? So that means the penalty is simply 0. So that means, okay, if your example not only is correctly classified, but also stays outside of my margin, then this max value is simply 0. We don't have any penalty, right? A second case is that, okay, if your example is misclassified, right, then what will be the value of function margin? Will be negative, right? Because y times this classification score will be negative. Then 1 minus some negative stuff will be definitely be positive, right? That means the maximum value will be the right term, right? 1 minus this function margin. So that means we will have an explicit penalty, which is 1 minus the function margin. This is the second case, right? So you can see that if you misclassify that example, you're going to suffer from some penalty, which is 1 minus the function margin, which is bigger than 1. Okay. And interestingly, we have the third case, right? Which is what you have just pointed out, right? Even your example is correctly classified, but it is within the margin. So basically means, okay, this function margin, this product is positive, but it's less than 1. In that case, you still have some penalty, which is 1 minus the function margin as well. This guy is between 0 and 1, but it's still some kind of penalty because it's not 0, right? So this gives us the so-called hinge loss function, right? So the hinge loss is defined as this max between 0 and 1 minus function margin, right? And the property of hinge loss is that, okay, only when you correctly classify and also your classifier correctly predict this example, and also this example is outside margin, you don't have any penalty. And you incorrectly predict the example, you got some penalty. You correctly predict example, but if the example is too close to a margin, you still suffer from some penalty. Okay? That's the property of the hinge loss. So give us a visualization, right? So let us first look at the red curve. This is called 0-1 loss. It's closer to our intuition about what a loss should be, right? If you make a wrong prediction, so by the way, the x-axis is this function margin, y times the classification score, right? So if you make a wrong prediction, it will simply give you 1. Right? If you make a correct prediction, you don't have any penalty. So that means it's simply 0. loss simply 0. And the hinge loss is different. Hinge loss is this black one. Now we can see that only when your classification score is bigger than 1, your hinge loss is 0. Meaning that when it's bigger than or equal to 1, it means that, okay, you not only correctly predict that example, you also is far away from that example. That example stay outside of margin, then your penalty will be 0, right? But between the 0 and 1, even you have a correctly classified example, but your example is too close to the margin, too close to the classifier, that means it's inside the margin, you still have some non-zero loss. In other words, you still have to suffer some penalty. Right? And then if you misclassify example, of course, you got some penalty as well. And also, the more wrong your classification score is, the larger the loss, the larger the penalty. So this is called hinge loss, and it is the uniqueness of the support vectors. So any questions so far? Everyone's comfortable? Okay. Right. So hinge loss, right? Incorrect predictions get a linearly increasing penalty with the size of the classification score, right? With absolute value of classification score, right? Hinge loss also penalize predictions even if they are correct, but too close to the hyperplane. That means they're inside margin, right? Hinge loss only gives no penalty when your example is far away from the margin. Okay. So now, from our SVM formulation, especially the soft SVM formulation, we can see our eventual loss has some kind of structure, right? One term is to maximize margin. Remember, maximize margin is to reduce the complexity of your hypothesis space, right? You can restrict the subset of linear classifiers over which you search. And the other term represents or describes or measures how you fit the data, right? That's why we call it hinge loss. Right? So you can see that, two terms, right? One is to penalize the complexity of your hypothesis space. The other is to penalize your misfit to the data, right? And then it brings a question, right? Can we define a general structure of your loss function design? Right? And yes, we have, right? And we can extend to the so-called general learning principle. Right? The first learning principle is called risk minimization. So what does it mean for risk minimization? We'll define the notion of loss over the training data as a function of a hypothesis. In other words, our loss only contains the term that fits the data. And the training is to find a hypothesis which has the lowest loss on the training data. One example is the least square of the least mean square for the linear regression. Right? We only minimize the loss to make our model to fit the training data as good as possible. Right? But here, SVM belongs to another learning principle. It's called regularized risk minimization. Right? So that means our learning objective not only contains a loss on the training data, it also contains a regularization term. This regularization term penalizes over complex hypotheses. And the learning is to find a hypothesis that has the lowest regularizer plus training loss. So you can see that your learning objective is to minimize a compromise between, regularization over the complexity of the hypothesis space and the training data loss. Okay? This is called regularized risk minimization. So going back to our SVM objective function, right? You can see that our regularization term is this half square norm, which essentially is to maximize margin, which is equivalent to penalizing overcomplicated hypothesis space. Right? And there's another term, which is called hinge loss, which is to measure how well you can fit the training data, right? And our learning is not just to make the training loss to be as small as possible. Instead, we're gonna minimize their summation. And we can design or we can specify a hyperparameter C here to control the trade-off between a large margin and a small hinge loss. Okay. And someone may ask, okay, do we only have one possible regularization term, or do we only have one possible loss term? The answer is no. Of course, you can choose whatever regularization term you want. You can choose whatever loss you want. Right? For example, and here in SVM, we specify square norm of W as our regularization term, which has a meaning of margin maximization, right? But of course, you can use any other regularization term you want. For example, in sparse learning, and usually people will use L1 norm of W. You want to achieve some sparsity of W, right? And in the training loss, you can pick up square loss, right? You can pick up whatever other loss, and hinge loss is just one choice. But overall, from the SVM objective function, you can extend it to a more a broad class of learning algorithms based in this structured regularized risk minimization framework. Okay, any questions so far? Okay, that's good. So now we have finished introducing the formulation of SVM objective function, right? SVM learning objective, right? And also from the structure of its learning objective, we generalized to what is the general learning principle we should take, right? And what is general structure we should consider. Right? So next, we're going to talk about how we solve those problems, solve those learning problems for SVM. How do we estimate WB? Okay, that's the topic for our remaining discussion about SVM. Then we're gonna talk about how do we solve the SVM optimization problem. Well, first to talk about how do we solve them from the primal domain, namely that regularization plus hinge loss objective function. And later we'll talk about if we want to extend our SVM to be nonlinearly classified, how can we do that? You'll see that we have to do a bunch of transform and to consider the dual domain and to look at the dual problem and solve the dual problem and introduce some trick. Okay. So we're going to use the stochastic gradient descent framework to solve the primal problem. Right? So here is our plan. So we want to review the definition of convex functions of gradient descent framework, right? We're going to review the stochastic gradient descent framework and look at what are the pros and cons for gradient descent and stochastic gradient descent. And later we'll see that actually we cannot directly compute the stochastic gradient for support vector machines objective because it is not differentiable. And then we can adapt our stochastic gradient descent to the so-called stochastic subgradient descent. Then we can literally doing training. So, okay, let us first review convex functions of gradient descent. So first, look at our SVM objective function. This function is convex in W and B. Right? And I will leave an exercise for you guys to show this. It's relatively straightforward, right? This function is convex in both W and B, right? And then for convenience, we're going to use a simplified notation. First, I don't want to explicitly write out the bias parameter B. So that means I'm gonna fold B into the weight vector W and then augment Xi with constant feature 1, right? We have used that a lot, right? At the same time, because in the first term, you only minimize the square norm of the weight vector itself. It doesn't contain B. So I denote the original weight vector by W0. Then after this notation simplification, we have the objective in this form, right? So the first term, it will have W0 transpose W0, right? And plus the hinge loss. So hinge loss now you write it as a max 0, 1 minus yi W transpose Xi, right? Remember, B is inside this new W vector, and Xi contains additional constant feature 1. Right? We're going to discuss how do we minimize this problem. Any questions so far? Okay, great. So, okay, convex function. What is convex function? If a function f is convex, then for every inputs in the domain, like u and v, and for every ratio lambda, meaning between 0 and 1, we have this inequality hole, right? So that is, if you pick arbitrary 2 inputs u and v, right, you use lambda to do a linear combination between u and v. You mean that their linear combination must be in between, right? U and v, right? You evaluate f at the linear combination of u and v here. This function value must be less than or equal to, you evaluate u and v separately and then combine their function values with lambda, right? Which will be here, right? So this is what this inequality means, right? Another important property of the convex function is that if this convex function is differentiable, then any tangent plane will lie below the whole function body. Right? So this inequality we have introduced this inequality before, right? So fx for any x in the domain will be no less than fu plus the gradient of u dot product with x minus u. So this is actually a tangent plane. Why is tangent plane? Why is tangent plane? Okay. Remember, you write the tangent line. It is the intercept, which is evaluation at some place, right? Plus the gradient of your function value at that multiplied with x minus u, right? This is the definition. This is slope, right? The gradient is slope. We just generalize to higher dimensional space, right? But this actually defines a tangent plane. So this just tells us, okay, the whole function body will stay above any tangent line or tangent plane on that convex function. Does it make sense? Okay. And here are a set of commonly used convex functions, like linear functions or convex function, and quadratic functions or convex function, and also the max function is convex. So max between 0 and x has a shape like this, right? You can use this definition to easily show that max between 0 and x is convex. But just be careful, the max function is not differentiable at 0 here, right? So you don't have any tangent line or tangent plane at this point. And for vector function, right? Say fx1, x2, this is a typical typical example of convex function as well. Right? This this cone, right? This cone is also a convex function, right? So there are several ways to show that a function is convex. For example, you can use the definition of convexity according to definition, or you can show the second derivative is non-negative, okay, which we have already tried, used in our homework 0, right? If your function is twice differentiable, and then you can show that for any point in the domain, the second derivative of your function is non-negative, then this function must be convex, right? Or if it's function, your input is vector, you just show the second derivative, which is Hessian, right? A is a positive semi-definite, then the function is a convex as well. And convex function, unfortunately, only takes a tiny portion of all possible functions. It's just a very small set of very nicely behaved simple functions, right? For example, this function and this function, they're not convex, right? And if in the definition, right, if you reverse the direction of the inequality, say, if your evaluation of the combination of the input is bigger than or equal to the combination of the function evaluations, right? This type of function is called concave function, right? Linear function is also a concave function, right? And if that's just to revert your quadratic function, it's a concave function. If you take minimum value of them, this is max, right? If you take minimum instead, it's a concave function. You can view like concave function is a kind of mirror to the convex functions. But many other functions are neither convex nor concave, like here and here. Okay, any question regarding the definition of convex function? I think everyone should be should not feel like strange or uncomfortable on that. And another thing we want to mention is regarding optimization. Usually, if a function is differentiable, right? If you want to minimize an arbitrary function, if x is a minimum for that function, then we can claim that the gradient of the function at x will be 0. So this is a necessary condition. It's not sufficient and necessary condition. Meaning that, okay, if a function has a minimum x, here the minimum means global minimum or local minimum, it doesn't matter. As long as the minimum and its function is differentiable, then at x, the gradient must be 0. This is called necessary condition. However, it could be that there's some x, its gradient to be 0, but it is neither minimum or maximum. That's why we call it, it's just necessary condition. It's not gradient 0, it's just necessary condition. It's not sufficient condition. One example is here. You got some 0 gradient here, but it's not minimum or maximum. But this will be the gradient to be 0 will be much stronger for a convex function. Okay? For a convex function, if you find the gradient to be 0, that means your x must be minimum and will be global minimum. Okay? That means the 0 gradient for convex function will be both necessary and a sufficient condition for you to find a global minimum of that convex function. Okay. So going back to the SVM objective function, right? We have already known that this function is convex in W, and this is called quadratic optimization problem because the objective is quadratic. see the W0 transpose W0 here, right? So that means you can use any convex optimization package, right? So quadratic programming, and to solve that problem, you don't need to write any line of code. And although you can solve that and guarantee to convert to the global minimum, it is pretty slow, right? And we want to introduce another commonly used, simple to implement, and also efficient method, which is gradient descent. Right? So now let us just quickly review the gradient descent. Gradient descent meaning that you want to minimize an arbitrary objective function, right? You start with some initial guess of your model parameters W, say W20, right? We just iterate until convergence, right? In each step, you just compute the gradient of your objective function at current model parameters, right? Then you update the model parameters by taking a step in the opposite direction of the gradient, right? Everyone has done that in our implementation of the least mean square regression, right? And here is example which we have seen before, right? Every time you just compute the gradient and then move the model parameters toward the opposite direction of the gradient. And as long as you pick up a right learning rate or step size, you're gonna eventually converge to the minimum of the objective function, right? So we can apply the same framework for SVM. Right? This is our SVM objective function, right? We initialize our model parameters, W, right? We denote it by W20. Then we go through many iterations. In each iteration, we compute the gradient of our objective function J at current weight vector WT. We call it nabla of G, right? And then we update W as follows, right? We subtract WT by the gradient multiplied with a learning rate R, right? Then we just keep doing this until convergence or maximum number of updates are finished, right? So this is a gradient descent framework, right? As we previously discussed, right? When you have a large number of training examples, gradient descent can be inefficient, right? Can be slow. Why? Because the gradient is to compute it by going over all the training examples, right? That means you go through a whole path of training data set, you only compute one gradient. That could be relatively slow, especially if your training data size is very large. Right? That's why in the practice, especially in the big data scenario, we prefer stochastic gradient descent. Okay. What is stochastic gradient descent? Yes, exactly right. I wouldn't say it's a lot worse. Yeah, in some cases, batch is better. In some cases, stochastic gradient descent is better. We'll talk about when and which one is better, and how we're going to choose this, right? But here we just want to review or refresh our mind about stochastic gradient descent, right? The gradient of SVM objective requires summing over the entire training set, slow, and does not really skew, right? So that's why we want to switch to stochastic gradient descent, right? In stochastic gradient descent, we're gonna run through many epochs, right? Each epoch meaning you pass through the data set for once, right? Inside each epoch, you pick up a random example, X and Y, from the training set S, right? You repeat X and Y to make a full data set, meaning that you kind of like use that single example to create a data set of the same size as the previous training set. Right? And then you compute the loss, the whole objective function on that fixed data set. Right? That means you need to compute this regularizer, right? And also because you repeat this xi, yi for many, many times, that means you just multiply its loss, which is hinge loss, by the number of times you repeat, right? Which is n. N is the size of the training set. You compute the training objective on this fake data set to get the gradient. And then use that gradient, which is we call stochastic gradient because it's not true gradient. You only actually compute them with a single example. Use that to approximate true gradient and do the descent, right? And here n is the number of training examples. And you update W accordingly, and you finish using one example, right? You look at another random example, you just repeat that for n times to fake a full data set and then calculate the gradient, which we should call it stochastic gradient, and do the gradient descent. Keep doing this until you finish our big T epochs, and then return the final W. So this is the whole framework. Any questions so far? I mean, if your original data set contains 1,000 examples, that means you have to repeat this single example for 1,000 times. That means you fake a data set to be of the same size of our original data set. And then you compute the loss, your training objective over that fake data set. That's why in our computation, we should multiply the hinge loss by n. N is the size of the training data. So you can see that there's a little bit difference from what you have done before, right? Previously, we don't have this operation like, oh, I want to repeat this, I want to duplicate this one. I just pick up one example just to compute the loss and take the gradient, that's it. And here we have to multiply the hinge loss by n. Why should we do this? What kind of change? Who causes the change? Let us explain this problem. Why should we do this? The reason is that in our objective, we not only include the loss term on the training data, it also includes a regularization term. So imagine that, okay, if we do things like before, you just pick up random example, I just calculate loss on that. That means only calculate loss on one example, right? Then plus the regularization term. And if you do the full gradient, that means you calculate the regularization term plus the loss over the entire training set. You can see there's a difference in terms of the skews. To match the skew, you have to multiply your loss over the single example by the size of total training set, and then plus the regularizer to ensure that your stochastic gradient to have the same skew as the true gradient. That's intuitively we should multiply it with n. Does it make sense? Okay. Any questions so far before we go to the detail? The reason we didn't follow what we previously have done previously, okay, if we find an example, like a random example, pick up a random example x, y, just calculate the loss on that example, take the gradient. That's it, right? The difference here is that because in our training objective, we not only include the training loss, we also include a regularization term, right? Then when you approximate the true gradient, you have to ensure your stochastic gradient to has the same skew or to match the skew of the true gradient. Remember, the true gradient is computed over the entire training set. It's just not only on one single example. So that means when you compute the stochastic gradient, although it's still look at the loss over one example, but you're going to multiply it to match the skew. Okay. And why should we match the skew? is to guarantee the convergence. So we're going to talk about the general framework about stochastic gradient descent. If your objective has the following form, you have a regularization term R plus the summation of the loss over n training examples, right? And the rationale of stochastic gradient as follows. I can rewrite my loss or my objective as R plus, you can see the summation here, right? I multiply each loss inside the summation by n, the size of training data, and then in outside I divide it by n. So it's totally equivalent to here, right? Because it just multiply n and then divide by n. But it gives us a different meaning. Imagine that I roll a dice, right? And I can randomly pick up example 1, 2, 3 until big N. And then this form tells us your objective function can be viewed as RW plus C times some expectation. That is, you randomly pick up one example, compute the loss, multiply with N, then you take expectation. Right? So here, the chance you pick up an arbitrary example is just 1 over n. That means the same for every example. Right? And if you look at the expectation, that means okay, you got a chance to pick up x1 to calculate loss, multiply n, or you got a chance to pick up x2, multiply n, and so on. Right? If you take expectation, it will readily recover your original loss, objective function. Does it make sense? You're talking about this one. Yeah, let us finish this first. Okay. So, but first we can see this. We can see this reformulation, right? We can see that your objective function over the entire training set can be viewed as an expectation, right? And why should we write it as an expectation? This is associated how we conduct the stochastic gradient. Right? If your objective function can be written as an expectation over some random objective function, right? Then you take the gradient. That means the gradient will be expectation of the gradient over your random objective. The stochastic optimization theory tells us that you don't need to really compute the true or exact expectation. You just need to compute the random gradient. As long as the expectation of the random gradient is the true gradient. When you use this random gradient or stochastic gradient to update your model, then it will guarantee the convergence to the minimum of your objective function. And more precisely, we should use probability language to tell that. That means it will almost surely converge to the minimum of objective function. Almost surely means that with probability 1. That's the whole theoretical foundation of stochastic gradient descent, meaning that you have to make sure that your stochastic gradient is an unbiased estimate of the true gradient. Unbiased estimate is that if you take expectation, it will be the true gradient. Only when you satisfy this, you can conclude that, okay, your leverage stochastic gradient to perform the gradient descent will converge. Okay, so we have delivered the key idea here, but I guess we need some time to connect them and to read, justify why should we do a duplication of n here. And we'll talk about that on next Tuesday. See you on next Tuesday.